Is there a better board? Can switch to that one maybe?
There's a chalk here.
No, I mean better board.
This is a chalk. Oh no, I cannot change it now.
Great.
1 second. I have a better chalk.
No, I mean a better board.
Sorry. Let's get it started. You are actually on that. Okay.
Oh wait, maybe the issue was the chalk. But there's a twist. There's a second spring attached to the first mass. So let's say this has mass m1, mass m2, spring constant k1, spring constant k2, and of course there's a downward acceleration z. What's the motion of these bodies? Well, let's think about it first. What are all of the forces on m1? Well, first of all, it's experiencing a force from spring 1. So let's call it K1. Let's say this is its rest position, and this is the rest position of x2. And yes, I know technically those don't look like the rest positions because it's going to be pulled down by gravity, but let's say that's their rest position if they were handled horizontally. There was no gravity affecting them. So K1 is going up this way, gravity is pulling it back this way, and spring 2 is also pulling it down this way. So let's call this distance delta kx1. Notice that m1 x1 double dot 1 minus k2 x2 minus g, or m1g. And then the second thing to consider is how.
Maybe you don't have white chalk. I don't see anything on the camera.
You just changed it.
Here.
That's the one I had to not stop using because it's so bad.
Oh, I found a chalk. Oh wow! You got lucky, baby.
That's also green.
No, it's a different type of chalk.
Yeah, it's brighter green. Oh, that's better. Okay. So let's see. Now you look at M2. Can you see now?
Yeah.
Yeah, it's clear now.
Do you understand the lesson?
No, I'm not a math person. Why are you asking me that?
Shame on you. Okay. So,
You have a twist.
well, who?
Your dad and your mom.
And if I gave you a test right now, would you pass?
I think so. I'm gonna practice them. Then I'll take the test.
Okay. So you have K2, X2 supporting it up. And you also have, well, not K1, X1 attached to it. So it's mostly just minus M2G. What did I step on? So now we have a system of two equations. It's not that bad so far, right? So we get x1 double dot is equal to x1 minus k2 over m2 x2, oh, m1 x2 minus g. Meanwhile, x2 double dot is equal to k2 over m2 x2 minus g. So how do we expect to approach such a difficult problem? Well, let's first start with a much more simplified case. What happens if both the masses and both the spring constants are the same? Well, you get a much simpler case of things because now all you have to do is, well, what happens if you add these two? You get m x1 double dot plus x2 double dot is equal to kx1 double dot minus 2mg. And that's pretty simple to solve, right? Now, what do we get here? Well, if negative mx1 double dot and write kx2 minus kx1 plus m1z or plus mg, and then mx2 double dot, which is kx2 minus mg, what do we expect to happen? Well, if you add these two, you get mx2 minus mx1, which is mx2 double dot minus x1 double dot, which is equal to k times x2 plus x2 minus x1 plus mg. So we can sort of define relative variables in this way. You can define, I don't remember how to do this topic. It's been really long. Okay, so now what can we do with these two equations? There has to be a better way to solve it. I'm sure this is not the way. Well, what is it? Okay. Let's see. So if x1 double dot is equal to k over m x1 minus k over m x2 minus g, and x2 double dot is just equal to, but I don't think these are the only equations, right? So let's imagine we held m2 still. What's the impact m1's position would have on it? Well, you notice that the spring K2 would keep lengthening and shortening even though M2 is not moving at all because M1 is still moving. That's the issue. That means that X2 is dependent on X1 in a very subliminal fashion. X2 double dot is dependent on X1. Sorry. So you get sort of a second force. For this lessening in force you get over here, you also get force lessening side of things because the total force exerted on this thing is k x2 minus x1. Now M2 doesn't have any impact on the springs that M1 is using, so that's that. M1 only has an impact on the kind of spring M2 is using. So you get k times x2 minus x1 minus mg. And suddenly, everything's way easier because now you just add these two up and you get mx1 double dot plus mx2 double dot. You don't even need to do that. X1 plus x2 double dot is just equal to minus 2g. And now, if you ask somebody what the individual ones are, x1 double dot is minus x2 double dot minus 2g, which gives you what? K. Now this would be simple. What am I thinking? Okay. If you subtract one from the other here, you get m x2 double dot minus x1 double times 2 1 minus 2 mg. Okay, great. So now I'm going to substitute in a new variable, I don't know, x. So that mx double dot is 2kx minus 2mg. And suddenly you realize this is just a differential equation, which you can solve with the homogeneous solution being what? You get m r squared is equal to 2k, And so that means r is equal to the square root of 2k over m. Which means the homogeneous solution is cosine of the square root of 2k over mt. And the inhomogeneous solution, which is just a constant solution, because you assume this is 0 and this becomes a constant, gives you c is equal to mg over k. So that's the movement of x2 minus x1. So we already noted down that x1 double dot plus x2 double dot is equal to minus 2g. Now what do we get from here? X2 double dot minus x1 double dot is clearly equal to 2k over m minus 2k over m cosine square root of 2k over mt plus no constant. And so, everything's going on today, huh? And so, you get x2 minus x1 double dot and x2 plus x1 double dot sum up to give you 2x2, which is equal to what? Negative k over m cosine rad 2k over m t minus g. Meanwhile, x1 double dot is equal to what happens if you negate this term first. And what happens if you do that is you get k over m cosine rad 2k over mt minus g. Okay, and you can also integrate, and of course the actual integration depends on the initial conditions, but I'm just going to say here that this is going to give negative 1/2 cosine rad 2k over m t minus half gt squared. And for x2, what? Negative half cosine rad 2k over m t minus 1/2 gt squared. Which means they're going to act like falling bodies, except they're going to oscillate while they're at it. And also think about the point of stability for a singular mass hanging on a spring. It's when mg is equal to kx, or in other words, when x, the displacement, is equal to mg over k. So we're kind of seeing that play out over here. It's going to oscillate around that point of stability. You get plus mg over k, the normal point of stability, plus cosine blah, 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 blah. So that's it. Thank you everybody for watching, and we'll see you in the next one. I completely forgot.